Now we will discuss in section 1.3 the integral calculus, and inside this integral calculus in section 1.3.1 we will discuss the line, surface and volume integrals. We know that in electrodynamics sometimes we encounter problems that are having a line geometry and sometime a surface geometry and a volume geometry. So for that, as we did in the differential calculus, some parameters we calculated, and now we will go on with the integral calculus, like what are the line and path integrals, the surface or flux integrals, and the volume integrals. So let's first start with the line integrals. So line integrals are path integrals. Line integrals are, this is also called path integral because it follows a certain path. So in path integral, we will write a path integral like an integral which is from one point, there is a starting point and there is an ending point, and for a vector quantity v or a physical quantity dot dl, this is a physical quantity, and as we are calculating it along the length element, so for that we use the dot product, the projection of this vector along the line element or the line element along this physical quantity or vector. Sometime we write here p as well in order to show the path integral, and if this path integral will be around a closed loop, then we will write this thing is a closed loop or closed path integral and v dot dl. The very familiar example of this is work. Work we write is from a certain point to another point f dot dl. So this is the work done along the length element, and we know that the path integral is critically depending on the path taken from A to B. However, there are certain functions or vectors which do not depend on the path followed but on the endpoints, like on the AB only, and those vectors or functions we will discuss later are termed as conservative vectors or conservative forces or conservative physical quantities, and electric field is one of it. Inside electric field, if work is done on a charged particle, then it is independent of the path followed from A to B. It will only depend on the end paths. So electric field we will say is a conservative field, or we will say the force involved in the electric field is a conservative force. So I can graphically plot this one. Let's say we are having our axes like this, that we are having the axes like the x, y and the z axis like this. This is our x axis, the y axis and the z axis, and let's say our function is like this, starting here and then moving like this. Now this is point A, that from point from where it is starting, and this is point B where this function is ending. Now any length element that I take along this one, means some length elements are there, and all the length elements, they are along this one, means the dot product will keep us to be on this function, and this will means at each and every instant, like v1 dot or v dot dl1, v dot dl2, v dot dl3, and so on. These are all the dls. Like I call this is the dl1, then this will be dl2, and so on, and it will cover this whole thing. I'm writing the DLs means in order to show them, otherwise the DL are so small that it's a fractional length. And when I write this thing in the integral, then it means here when I write this thing in the integral, it means I'm calculating area under the curve. So this is the area under the curve, and it will be like this area is covered here. This is the area which is covered, and similarly all this area is covered here, and we will have something like this. So this covers all the area, means the area covered under this function. And that's the beauty of the dot products. We cannot write, as these are two vectors, we cannot write them without the dot product, as they both are vectors. So this way, this is giving us the line or path integral. And now we will solve an example on this one, which is example 1.6. And this example is, let me read the example. Calculate the line integral of the function v equal y square in x plus 2x into y plus 1 in y direction from the point A 110 to point B 220 along the path 1 and 2 is shown in figure. What is the closed loop integral v dot dl for the loop that goes from A to B along path 1 and returns to A along path 2? So first I will draw this figure, and then we will we will solve this figure. So the figure is such that we are having the x and y, means it's a plane geometry. So we are having the x and y axis. Let me draw this one. We are having the x and y axis. This is x axis and this is y axis. Now here, if I grade this one, then let's say that this is point 1 and this is point 2 and this is point 3, and here similarly this is 1, this is 2, and this is 3. Now it says that point A is 1, 1, 0. So this is 1 and this is 1, so it is over here. This is point A, and point B is 2, 2, 0. So point B is here, 2, 2, 0 here. And then we are having here the path 1. So it is something like this. This is 1, this is 2, and this one is path 1, this is path 2, this is point A, this is point B. The coordinates of the point A are 1, 1, 0. Point A is at 1, 1, 0 here, and point B is a 2 2 0 here. Now the function that we are having is v equals y square and x plus 2x y plus 1, 2x into y plus 1 in the y direction, and we are supposed to find out the v dot dl along path 1 means from here to here and then here to here, and then from b to a along path 2 we will have to find out the difference. So note that what about dl? dl is a length element, usually in 3 dimension. We are having it dx in x unit vector plus dy in y unit vector and plus dz in z unit vector, but here we are having planar geometry of x and y plane, so dz is equal to 0, and we are left with dl, this one. Now if I consider path 1 here, means inside path 1 I consider this Roman 1 here, and what about dl here? dl here is equal, it is only going along x, so it means the dy is equal to 0, and I'm having dx along the x unit vector, while dy along this is equal to 0. And when it is running, let me write 1 and 2 here and 3 here, similarly 1 2 and 3 here. So when it's running along the x, the y value is equal to 1, so y is 1 here. Now calculate v dot dl, and v dot dl is equal to, we are having only x here, so this is y square dx. This is y square dx, and we know that y is equal to 1, so this is equal to dx. It means when we will do integrate, v dot dl, and then this is equal to dx. And what about the points from where it starts and where it ends? It starts along the x from 1 and ends on 2, so this is from 1 to 2, and the answer is x from 1 to 2, and then this is 2 minus 1 and is equal to 1. Similarly, we do calculate along part 2. In the path 1, we calculate the second part here, and in this one, the dl value is equal, when we are moving from here to here, only y is changing, so it is only dy and y, while the dx is 0. dy and y, while the dx is equal to 0. And when we are going along y, the value of x here is equal to 2. So x is equal to 2 here when we are going along y. So what about v dot dl? v dot dl will be, this is v and dl is just y, so this term is 0 and this term remains, and this is equal to 2x into y plus 1, 2x into y plus 1 here. And we know, because y dot y, it will becomes 1 and dy here, so this is 2xy dy here. And now I can calculate the rest, as I know that x is 2 here, so this is 2 into 2 becomes 4 into y plus 1 and dy. Now I can integrate this one. So integral v dot dl is equal to integral 4 into y plus 4 into dy. 4 into y plus 4 dy is equal to find out this thing. Now I know that when I'm moving along y, then how much y is changing? It is changing from 1 to 2. So the integral limits are from 1 to 2 here, 1 to 2 here. What this will be equal to? It will become 4y square by 2. So 4y square by 2 from 1 to 2 here, and then plus 4, and dy will become y, and from 1 to 2 here, and this one comes out to be, if I do simplify this one, then 2 ones are 2, 2 twos are 4, so I'm having 2, and then put the limits, 2 square, so 2 square is 4, minus 1 square is 1, and plus 4 into 2 minus 1 is 1. So the v dot dl comes out along path here. This one is 1 and this one is 2, and this comes out to be equal to 3 into 2, 6 plus 4, and this one comes out to be 10. So along path 1 and along path 2 means the path 1 here is actually equal to the sum of path 1 plus this is part 2 here, and this is equal to 1 plus 10, and 1 plus 10 is equal to 11. And now we do calculate along path 2 here. So for part 2, let me write here, for part 2, what is the situation? Vector is our this one, and I know that along part 2 the dl is equal that both x and y are changing. Now the dl will be dx and x plus dy and y. It will be now both will exist here, because in the xy plane this is now a tilted line, so it means it is having both x and y component. So do multiply v dot dl here. V dot dl will multiply here like y square dx, y square dx here, and then 2x plus y1, 2x and y plus 1, and this will be dy here. So we have our equation like this. Now we can change here. We can come to one variable here, and to come to that one variable I will check here that this is from 1 to 2 and the y is also going from 1 to 2. It means along this line this x and y are the same, both are varying from 1 to 2, 1 to 2. So it means that x is equal to y here. So put in this one either y equal to x or x equal to y, and then we will have our integral. So v dot dl from here is equal to x square dx, and this will imply that dx is equal to dy as well. Dx, then 2x plus x plus 1 and dx. So I can now simplify this one. this will be then equal to x square dx and 2x square dx. So it is 3x square dx plus 2x into 1 and 2x dx, while x is changing along this line from 1 to 2. So the limits are those. So let me do calculate v dot dl integral, and this is equal to integral 3x square dx, and x is running from 1 to 2 here, plus 2x dx, and the same 1 to 2 integral, and this is equal to 3 into x cube over 3, 3x cube over 3 from 1 to 2, and plus 2 and x square over 2 from 1 to 2 here. Now 3 is cancelling with 3 here and 2 is cancelling with 2. So we are having x cube minus, means this will put the limits. So the first one is 2 cube minus 1 cube, and it is 1, and plus then 2 square minus 1 square, and we have this one 8 minus 1, so we have 7, and then 4 minus 1 is 3. So the answer for the part 2 comes out to be 10. Now in the example, it is being asked that you go through path 1 and then you return to part 2. So it means that it is actually the closed loop integral from a to b and then from b to a, and v dot dl, and this is equal, as we had here this thing equal to 11 path 1, this is path 1 and this one is 10, so we have 11 minus 10, and this comes out to be 1. It tells us that the vector function that we are having here is a non-conservative function, a non-conservative vector, because it strictly depends on the path which is being followed. If it would be independent of the path, then we would have got 0 here. So it is a non-conservative force, and we can check this one by calculating del cross V here, and then del cross V will not be equal to 0. If it would be equal to 0, then it would be a conservative force.